Hello, everyone. Thanks, Varun, for inviting to this session. Uh, so today I'm going to talk about a recent line of work that I've been interested in. Although the title of the talk is title of one paper, I'll be essentially summarizing three related works. Okay, so the first model considers a system of n servers connected by some graph. Each server has its own queue, and each queue has an arrival process, and the arrival process is a person process with rate lambda. Now, whenever and independent of all other arrival processes. Now, whenever a task arrives, say this green task, it looks at all its neighboring queues, including itself. So these four queues, and it assigns the task to the shortest of those queues. Now, after the service, tasks leave the system, and also note that only external arrivals can look at the neighboring queues and can be routed. But as for example, in this case, the green task, it cannot be further routed to its own neighbor, so it can be routed only. It will wait in this queue until execution. Okay, and the graph is fixed once and for all, and this can be contrasted with the resampling of servers per arrival in the usual load balancing type of cases. Now, if the graph is fully connected, then this is the classical join the shortest queue policy, where each arrival looks at the whole system or all the servers, and it joins the shortest queue. There are several motivations for considering sparse graph. We will mainly focus on task server compatibility constraint. Basically, executing a task at a server requires some pre-stored data or specialized skills. So, and serving all task types usually requires a huge storage capacity. Consequently, the arrivals, you can think of it like that arrivals at server I can only be assigned to a subset, say an I of servers. Now, this subset can be viewed as neighbors of some neighbors of vertex I in some underlying graph G. And sparsity is desirable because the storage capacity of the server can be roughly viewed as the number of connections of that server, so the degree of that server. Our goal is to answer the following question, that how much sparsity can be allowed by retaining the asymptotic behavior of a click. Okay, and we will look at the asymptotic regime as the number of servers n tends to infinity. Our main quantity of interest is QI-GNT, which is the number of servers with queue length at least I at time t. So just to visualize, if you arrange the servers in non-decreasing order of the queue lengths, then QI is essentially the width of the ith horizontal bar. And we'll denote the corresponding fluid scaled quantities or the fractions by the corresponding small letters. And note that this process is non-Markovian, and essentially that there is no no classical asymptotic analysis techniques would work here, and that poses the main challenge. And by fluid limit, we'll refer to any weak limit of this QI process as n tends to infinity. Okay, now our first result is to characterize the limit for a deterministic sequence of graphs, limit of this process for a deterministic sequence of graph. For that, let's define a measure of well-connectedness. So for a given graph and a given subset U, define this com U to be the number of vertices that are completely disjoint from U. So for a particular subset, you look at first subtract from the whole network, subtract U and its one neighborhood, and whatever remains, the number of vertices in that set is basically this com U. Now, this measure of well-connectedness is saying that if we look at a set U, like supremum over all sets U, which are of some mass, okay, some positive mass compared to the whole network, then the maximum cardinality that we can get, maximum cardinality of COM-U. Okay, so that is basically this well connected, this D1 quantity, and with Sam Borst and Johan van Leeuwarden, what we showed is that any graph sequence will have the same fluid limit as the fully flexible system, as the clique, if this D1G epsilon is a small o n for all positive epsilon. Okay, that means in informal terms, it says that in your network, for large enough network or large enough n, if we take any large enough part of the network, then the set of vertices that do not share any edge with that set is negligible. Okay, so in the beginning it may seem a bit strict, but if we consider random graphs, for example, what we showed is that if the graph is random in the Erdos-Shreni sense or random regular sense with average degree Cn, that means average degree Cn for Erdos-Shreni and exact degree Cn for random regular, then the graph is fluid optimal for any growth rate of Cn. So for the clique, the degree of a server is n-1. Whereas this theorem says that any growth rate from n-1 to any growing number is enough. So the graph becomes substantially sparse, provided maintaining the asymptotic performance of a clique, provided they are suitably random. Okay, so that was the first result. And one key ingredient in the proof was monotonicity of the performance with respect to edge addition. That means we heavily use the fact that in a graph, if we add more edges, that means we make the servers more flexible, then the performance becomes better. And things become significantly more challenging if this monotonicity is not present. For example, one such model is if we consider JSQD instead of pure JSQ. That means at each arrival, now say D is 3, then at each arrival, D-1 neighbors, random neighbors, are selected. In this case, the green task selects these two neighboring queues, and the task joins the shortest queue among the where it first appeared and its two random neighbors. Okay. So now this is for brevity, we can refer to this model as JSQD on graphs. Now, again, if the graph is a clique, then we get the classical JSQD scheme. However, in this case, even the optimality of the clique is not clear. That means it is not clear that among all possible graphs, the full flexible graph, the clique, will have the best performance. Such a statement is unclear due to the lack of monotonicity. Okay, however, we show with Amarjit Budiraja and Ruoyu Wu, we show that if the system starts from a good state, roughly meaning that the queue lengths at each server is their IID basically. If they start from a good state, then the fluid limit of the system on any finite time interval will coincide to that of the clique case. If the minimum degree diverges and the graph is almost regular in the sense that the ratio between minimum and maximum degrees that converges to 1. Consequently, observe that if the graph is regular, then the second condition is trivially satisfied. As a result, the graph we get this result for any growth rate of Cn, the average degree. Here it's exact degree. And if the graph is random, like Erdos-Shreni, then this condition can be satisfied if the average degree grows faster than log n. The proof here uses a coupling approach, coupling with an infinite dimensional Mac-Lazov process. The good starting state assumption appears to be a bottleneck to prove steady state behavior. As a result, this result is only the process level convergence, and the steady state behavior was open in this work. Now comes to the we are here at the third model. This model, this is a recent work with my PhD student Dan Ruten, and I'll mention the reference at the end. So this model actually considers the task server compatibility case in the following. So we have a set of task types Wn, and number of task types is say Mn, and we have a set of servers, and the number of servers is M. Now we have a bipartite graph between the task types and the servers, meaning that if a task type shares an edge with a server, then that server can serve the corresponding task type. For example, here server 2 is able to serve task type 1 and task type 2, and so on. Okay, the arrival rates, the arrival processes are Poisson processes with arrival process of each task type is a Poisson process with rate lambda n over mn. Here we consider homogeneous rates of arrivals. The total effective arrival rate is lambda times n, and the service time distribution of each task is exponential with mean 1. And we'll be looking at an asymptotic regime where both n and mn tends to infinity, although we don't restrict to any particular growth rate of n and mn. This is general. Okay. We should mention that this model with inhomogeneous arrivals and service rates has been recently considered, in fact, contemporaneously to our work by Wang, Zhu, and Srikanth. Okay. However, their goal is a little bit different. They are interested in obtaining asymptotically vanishing delay performance, whereas we'll be interested in JSQD type performance and process level analysis and steady state analysis and so on. Okay. Now we will consider JSQD for this restricted structure. That means each arrival selects D compatible servers. Suppose a task of type 3 arrives and suppose D is 2, then it selects 2 random compatible servers, 3 and 5, and the task joins the shorter among those 2 servers. Okay, so now what we do is for a deterministic sequence of graph, we introduce a notion called proportional sparsity. So let's explain it carefully. So what it means is that first fix any task type, say W, then look and any subset of servers. Then look at the fraction of its neighbors that go inside U. So this is this quantity, that the neighbors that are within U divided by the total number of neighbors. Okay, so this is the fraction. So in this case here, its number of neighbors is 2 and only 1 goes inside, so it's half. Compare this quantity to the size of this set U. Okay, so here it is also half. Okay, so what we need is for most task types, where by most I mean that almost all except a small o mn. So mn is remember, mn is the number of task types. Only small o mn task types we can let go. Other than those, for most task types, these 2 quantities are not far away. Okay, to formalize this, what we say is that for any positive epsilon, the fraction of task types for which these 2 are very different, that is asymptotically, that goes to 0 as it tends to infinity. So that is the definition of proportional sparsity. What it means is that the graph can be sparse, but it has to be sparse in a balanced way. So this is one thing I should also mention, that if you put epsilon to be 0, then there is only one graph that satisfies this condition, that always for any subset these 2 are the same, and that is complete bipartite graph. Now it relaxes that condition in 2 ways. First, It allows a little bit wiggle room between these two quantities, small wiggle room, and also it is okay if it lets go a few task types. And we'll see suddenly there are huge number of sparse graph structures or sparse compatibility structures that actually satisfies this condition. Okay. So what we show is that if a graph sequence is proportionally sparse, then the fluid limit of the system coincides with the complete bipartite case. Sorry, this is a typo, it's not click, it's a complete bipartite case. And I should also mention that for this fluid limit result, we don't only consider JSQD, although I just mentioned JSQD only. This is true for arbitrary Lipschitz continuous task assignment policy, meaning the assignment policy should depend on the depend continuously or smoothly enough on the empirical Q-length distribution. I can talk about that in the Q&A session if you are interested. Okay, and we establish both process level and steady state results. Okay, so I'm almost out of time. We show that for if the graph is random, like if GN is constructed by selecting DN task types randomly for each server, then the process level and steady state behavior coincides with that in the complete bipartite case if DN grows faster than Mn log n over n. So this is the growth rate, and DN must go to infinity. Okay, so this is, and we also allow consider the case when the number of connections per task type is very inhomogeneous. Like few task types may be important, they may prefer more flexibility, and few task types may be less, so and they may prefer less flexibility, and we capture that case as well, but I will not go into that details. Okay, and here are the references, and this is the latest work with my student Don, and it's going to appear in Sigmatrix next year. And if you are interested in this work, particularly in the new work, then I definitely recommend you check out Don's talk, and where he explains this in more detail. And with that, I'd be happy to take any questions. Thank you so much for your attention.